on the Pacific Coast. It's about time to get started. Uh, Thank you for joining me today. We're going to be talking a little bit about command and control channels and kind of what they do and what they're for, how they work, why they're a pain in the ass, etc. And kind of as a visual aid to walk through that, I had written a really crappy C2 as a kind of analyst test for people that we interview. I do a packet dump of the C2 itself and then say, hey, like what's happening here? Kind of answer some questions about it. It's not great. I'm still working on it to make it a little bit better. And then once I get it reasonably functional, I'll probably put it on GitHub, just kind of play around and let other people contribute to it. And maybe I'll learn some stuff. Maybe they'll learn some stuff. Everybody learns a bunch of stuff. So as a quick intro to what C2 is, or command and control, CNC, we're all kind of the same names. At the basis level, they're a way for a compromised computer to talk to the controller. And what that typically means is that it's some sort of obfuscated method. It's a non-standard channel. They're not just opening up Telnet and saying, well, what should I do now, master, kind of stuff. It's usually hidden in some way. So what we're currently looking at is, I'm not a developer. This is some code that I wrote, some Python code, and it is a ICMP based command and control channel, meaning that it will ping out, the client will ping out to a to its C2 server, its command server, and say, hey, do you have any messages for me? Do you have anything for me to do? The server will decide if it does, through a couple different methods, and then send back the command or nothing. If it sends back a command, the client will run the command, and then the next time it checks in with the server, it'll say, hey, here's the output for the command that you wanted me to run. And we'll kind of see a few more details about it here. So we import some stuff. The most important one, of course, is Scapy. One of the things I'll be doing to kind of update this is rewrite the whole thing in sockets, because Scapy is kind of a pain on Windows, and I want this to be cross-platform. But what Scapy is a kind of high-level abstracted way to deal with packets and packet information. You can create packets, you can read packets, analyze packets, do all kinds of crazy stuff. Way more than what I'm doing here, but it's worth looking into if you're not familiar with Scapy at all. We have the main function, the kind of meat of what's happening here. We define these things called keys. They're just pre-shared keys, so that when their communication is happening, the server or the client knows that it's coming from the other side. And obviously dead beef and dead are easy to spot if an analyst is just looking at stuff. But again, this is just an example. Likely you'd have some actual keys, a little more interesting key. Maybe you're doing some sort of key exchange rather than a pre-shared key, so that you can do like a public-private key sort of infrastructure. Asymmetric key use would be cool. This is, again, just an example. We set up our socket, our listening socket, on the server. One of the things that I had to do for this particular piece of software is I had to disable ICMP on the command server completely, so that when it received a ping request or an echo request, it didn't just automatically send an echo reply back before the C2 server could kind of process and figure out what it wanted to do. So this particular server is not running, it has ICMP disabled through some CTL stuff. So we set up our own ICMP socket, raw socket, and then we go into this infinite loop. And what we're doing is the first part of our payload will always be the server key. Then we say, okay, let's receive a packet, and this is the max packet size. So we'll receive a packet, And then just some debugging text. I have this in here. This program is not finished. I'm in the middle of updating it, and I couldn't get it working the way I wanted. So about 10 minutes ago, I said, screw it. It works good enough. We're just going to keep moving on. But I still have a lot of my debugging prints in here just to kind of see where things are breaking. The Scapy packet, this is basically a disassembled interpreted packet. It's not in its normal binary. It's in various different strings and callable strings. Specifically, we can take Scapy packet and then we can go into the ICMP portion of the packet, the ICMP headers, and then we can get they call it raw, which is not the headers themselves, but like where the payload and whatnot is. So we go in here and we say, okay, if the request had more than just the client, or if the request has the client key, then we can keep processing. Then we take a look at the ID and the sequence number, so that when we return, we can return the same ID and sequence number that we received. We look at the source so that we can return it to the place that we got it from. And then we see, was there command output included, or was it just a check-in? So if there was command output, then we send it off to this process C2 call function. And all that really does is take the output of the command that we had it run and then write it to a file. That's it. So that we can keep track of the information that we're getting. Typically, these C2s operate over a long period of time, or they're not necessarily like actively being managed at all times. They're just kind of running, and servers check in and they get their instructions, and then they give the output whatever they want. Somebody's not necessarily behind a keyboard staring at the monitor 100% of the time. So this is just kind of write it out to the file so that I can check it later as things develop. So where were we? Okay, so there's the call. And then we have this thing called is C2 appropriate? And that's a weird name for it, but really all this is doing, if we look up here, is it does a random check, and if the random is 50% of the time it's going to say true, otherwise it's going to say false. And actually, I usually have this set to like 20% of the time it says true, or 10% of the time it says true. We'll get into why that's important in a little bit, but the point is that it's not always responding with commands, even if it has a command to send. And so then it checks to see if it's appropriate, and it says, you know what, yeah, it's time to send a new command. So we find the next command. All this is doing is it has a command and control list of commands, and we'll actually bring that up. We have this list of commands, and the first thing we want to do is ID. Who are we on this? Since we pushed up our shell, see who's available. We'll create our own user ID. Preferably in group ID 0, maybe. And then we'll make sure that our user add worked. We could add commands to this manually by like echoing something to the end. So we do like echo sudo -l to the end of command list. And that's how we'd add commands to the command queue, right? So, now as the C2 processes, it'll process all these, and we'll add something new. And then we decide something else we want to do, we can just do the same thing. Eventually, I'll probably have some sort of web interface where I can through an REST API call or something, I can post commands to that, and then it would be added to the file, or however. I haven't decided all that, but I want something that I could run in like AWS or somewhere on a VPS somewhere, and I wouldn't necessarily have direct access to it. I'd REST API it up or something. But yeah, so this is just processing the command list itself, and it says, okay, give me the next command, and then move forward. So it gets that command, and then as long as there is a command, basically it's not just returning new line or it's not returning blank. Then it says, okay, we're going to base64 encode this for other reasons that we'll get to in a little bit, and then create this packet. And so the creation of the packet is put the IP source, or put the IP destination, the packet ID, the ICMP ID, the ICMP sequence number, and then the payload itself, which is the command that we're having it run. And send just sends it. So that's it. That's pretty much it. Oh, sorry, it does this generate packet, and you can see. So, it takes in this. So the packet destination is going to be the source, the original source, and then the ID and the sequence number, and then the payload, as you see. And then it creates this. This is the syntax for creating a packet inside of Scapy. It's really straightforward, as you can see. Here's the IP header, and you can put whatever you want, whatever works in IP header. In fact, let's boot up Scapy real quick. If you guys saw my the Lord of the Root boot to root videos, then you might have seen us use Scapy for port knocking, but just a quick overview. If you look, you can just run, once you boot into Scapy, which is kind of a Python-like interpreter. Scapy is Python, but the Scapy interpreter is kind of tricked out specifically for Scapy. So we can see what is available inside of the IP header. So we can set our own IP flags. We can set whether or not we want the IP packet to fragment, what the custom TTLs, which protocol is using. In our case, it's ICMP. Checksum, we can set our own checksum if we want, source, destination, et cetera, et cetera. So all you're doing is just saying, I want to create an IP header with these things in it, / and then the next one, which will be the protocol. So the ICMP. ICMP type 0 is a echo request. It's got to be an echo reply. Let's find out. I think 8's the echo request, and then the code is different stuff. I wish it would tell us here. I think ICMP type 8 is echo request, and then ICMP type 0 is echo reply. So, which is why the server is sending a 0. What our ID and sequence numbers are, and then the packet payload, and then we return the packet, and it gets sent. So that's that. We can take a look at the client, which is a lot more simple. So the client pulls in some stuff. Again, Scapy. I don't know why that's in there. That must be from something old. It will. It's got its payload, which is blank for now. It recognizes the pre-shared keys, of course. We've got our infinite loop here. So we send a ping with the payload of the client key and the client key, which is here, and the payload, which is currently blank. And we set C2 response equal to that. So when we get a reply, where's the send ping here? So we create this ping, and then the way we send it is we use SR1, which means that we send and then receive one packet as kind of our operation here. So we send and then we only receive one packet, and that one packet is saved in echo reply. And then we return, as I mentioned earlier, we return the raw ICMP payload only. That's what this selector here is. So C2 response is set to this ICMP payload. Then we make sure we say if it's longer than 10, because our pre-shared key is 10, and the first 10 characters is the server key, making sure that it's a server reply. Then we say, okay, there's a command here, and then we want to do execute command. So this is a little weird, but what we're doing is we're base64 decoding the command, because if you remember from the command and control server, we're base64 encoding all of our traffic, right? So we decode the response and then send it to this execute command function, which is really just running the command on the local server and then returning the command output. Then we're saying base64 encode that, and that's our new payload. So when we go back up to the top of this infinite loop, we have a new payload, basically the reply to send to the server. So that's super straightforward. And then we've got the sleep 5 Generally, what I like to do is sleep for a random amount of time between 0 and 31 seconds, or a minute or 5 minutes or whatever. And the reason for that, if you recall, on the server, we had a similar kind of functionality where we say, is C2 appropriate? Where we kind of decide, 50%, 20%, 10% of the time we'll actually give a C2 command. There's a couple reasons. The main reason is this, that when you are a defender and you're trying to find command and control traffic, and specifically command and control traffic that is kind of obfuscated like this, whereas using ICMP, like irregular ICMP packets to kind of exchange data, you can't just alert on every ICMP packet that enters or exits your environment. You can write some, more complicated rules to check on payloads, but there's ways to get around that too from the attacker's perspective. So what's something else you do? Well, a lot of times command and control channels are regular. Every 10 seconds, every minute, every 10 minutes, whatever, they check in and do their business. And so defenders have been developing ways to do basically beacon detection and say, hey, we see, an ICMP packet going out to a collection of servers every 10 minutes on the dot, no variation at all. And then that helps you kind of helps you detect command and control stuff like this. If you randomize it a bit, if you give it like only a 20% chance of responding, or on the client's only checking in, random times between a minute and 10 minutes or something like that, it's much harder to do that beacon detection. So we kind of build that in just to make it a little easier to bypass, detection. Another thing that we do, for that purpose is we base64 encode and decode stuff. Intrusion detection systems can be set up to be looking for commands being sent over the wire. And base64 encoding can help disrupt that. Probably what we'd rather do is actually use some form of actual encryption. And while that's a little more heavy-handed and easier to detect, it doesn't actually tip off the defenders on what is happening. And if you've ever participated in an incident response, it makes your response much more effective if you actually know what's happening, what got exfiltrated, what the attackers are doing. It helps you build your timelines. It helps you focus your response in areas that need it, rather than kind of going over everything with a fine-toothed comb. So all of that is important. There's another kind of interesting way is, excuse me, instead of just encrypting or encoding like your payload, I've seen people encode their command and control traffic and responses inside of the, where are they at? Inside of these two fields, the ID sequence and ID and sequence numbers, or even just anywhere else in the headers. You can find something in this header that doesn't necessarily matter. Checksum, for instance, checksum could have the potential of getting, dropped midway through the conversation, but, somewhere else. Yeah, I don't know. Some of these other fields might not be used as much, and can hold data, like encoded data. But so let's talk about some of the other things, other types of command and control traffic that I've seen in the past. I've seen other ICMP command and controls, specifically ones that work better than mine. The stuff I was talking about where they encoded, the data into the ID or sequence headers or other headers, makes it much more difficult to detect. Additionally, DNS, people will encode command and control traffic in the subdomain of a domain that they control, and then use the DNS resolution requests to communicate with that domain controller. And there's a custom, bind script or something running that takes the the requests and then interprets them in some way and then sends some sort of reply to them. So again, command and control using DNS, you can't just block DNS either, right? So the goal of these command and control channels is twofold. Use a protocol that you're not going to be able to just turn off, and two, embed themselves in that protocol in such a way that it's very difficult to distinguish that traffic with legitimate traffic of that same protocol. At least in an automated fashion. Maybe manual analysis it's easy to point out that, like, okay, well, this isn't matching up right. This doesn't look like a normal DNS request, or, this domain name is like 80 characters long, and who really has like, hex 80 characters of hex in their domain. But from an automated perspective, it's a little more difficult to write those rules. And with those two goals, the common protocols and hard to detect, one of the other command and controls that I've seen in the past that is basically impossible to detect is a Gmail command and control channel, where you essentially set up your own Gmail account for this purpose, and then it communicates using Gmail, messages and API calls. And that does two things. First of all, everyone has a Gmail account or, some sort of Google account. And, blocking that is nigh impossible. And in fact, a lot of companies these days that use SaaS for their file sharing and email accounts and whatnot, they might be a Google Apps customer and they're literally using it for their business. And then on top of that, Gmail is all HTTPS. It's all encrypted. You're not going to see what's happening in there without seeing everything that all your employees are doing all the time, right? So even if you employ something like Palo Alto's man in the middle, like SSL decrypt functionality, I can almost guarantee you, while you're socializing that to your business units, the one concession that you make is let me close that. The one concession you make is that you don't decrypt like financial data, you don't decrypt medical data, and you're probably not going to decrypt Google because the execs aren't going to want their email being decrypted. So Gmail will always be encrypted, and it will always be used, and it will be pretty freaking impossible to detect like a Gmail command and control. If I remember correctly, it's called GCAT. I want to say it's called GCAT. Yeah. So here it is on GitHub, ready for you to use and, in your engagements. But man, this one is, and won't be updated. Oh, that's unfortunate. Okay. So yeah, maybe GCAT's not the one anymore. Well, there's other stuff out there for you to find. That's fine too. But so I kind of alluded to the real problem with C2 earlier is that they are extremely difficult to detect from a defender's perspective, which is kind of their point. You have to set up, like my ICMP C2 that we went over is pretty easy to detect because most operating systems have, their default ICMP payloads. And, I think like Linux is just a sequence of hex characters that go from like, I think it's like 50 through 70 or something, and then you'll see like an A through Z and 0 through 7 or something. If you look at the payload of a Linux ping. So, with IDS and IPS, you can kind of determine what the standard ping should look like and just, notify or block any non-standard pings. You can't do that for all ICMP messages, so things like, MTU path discovery might use different payloads or different, payload sizes to, determine what the MTU of the various hops in the path are. So even just ham-fisted, nothing with a payload over than 20 bytes is really going to work out for you. It might break things in your network. But once you start getting into the more advanced stuff, like some of the DNS C2, or like I said, the Gmail C2, it gets pretty freaking impossible to detect. So that's where you start moving towards beacon detection, like I was telling you about. Black Hills Information Security puts out a tool called Rita, which is basically for that. It's a hunt teaming tool, but one of the things that they've showcased a couple times in webcasts is their ability to slurp in network logs and like NetFlow data and whatnot. Use that to detect beacons. Like we're seeing, the same host over the same protocol to a the same destination or same set of destinations, like every 30 seconds on the dot, kind of thing. And you can start finding those detections, or start finding the C2 traffic that way. But once the attackers start using something like a randomized check-in time, and then also don't respond with the command every time it reaches out, like maybe just wait for a little while, kind of stuff, it really starts throwing off that static beacon detection. And you as a defender, you have to start going into some sort of anomaly detection, statistical analysis of, okay, this is what our normal traffic looks like, this is what our normal behavior looks like, and here are things that are kind of outside of that norm, and it gives your analysts a place to start looking. Now, how that can be done against a Google or Gmail command and control channel at a Google Apps customer site, I don't know. That's a question that I'd love to discuss and figure out, and kind of maybe meet with some of you guys at a conference and discuss it over a couple drinks. But that is a hard question to answer, and I certainly don't have those answers at this time. But we've pretty much hit everything I wanted to talk about with C2. Obviously it's a pretty expansive field, but I wanted to just get our feet wet here, and just kind of get people thinking about C2s, how they operate, kind of what their purpose is, more than just to check in, but like what they consider successful in C2s. And then also show you how easy it is to kind of write your own. This thing is obviously malicious, but it really has no malware signatures, or it won't get caught by anything because it's just a Python script that runs system.call. So what are you going to filter on for that, or what signature are you going to write for that? You can't really. It's just a text file. So it's not super hard to do. And in fact, let's just run it real quick. So the C2 is running, and if you recall, it's going to read from this command list. We're going to clear out the C2 output, because that's where the command output's going to go. But so that's up, and then we'll go over to the client. And we will is it in? Yeah. So it's outputting. So we can kind of see the stuff, and here's that first list. So let's go ahead and kill this, just because, like I said, it doesn't work very well. Once it gets, I think, like 2 or 3 rounds of that client response stuff, it just goes nuts, as you can see. But we can kind of see what's going on here through the debugging output. So we received a packet. We looked at it. It has the client. It has the client key, so we know it's a packet from the client. We checked to see if it was appropriate to send command and control. It was. So the next command is ID. So we generate the packet and we send the packet. Now this is what the binary headers of an ICMP packet look like, without actually decoding them. and then here's the payload we're sending. So there's the 0x dead, and then AWQK is base64 for ID. So then we kind of wait, or then we send the packet. This is the packet we generated. We sent it. It's sent now. Then we wait, and then we got another packet. And this is what we got for the packet. So here's dead beef, which is the client key. And then AWQK is ID, of course, and that's the command we sent it. And then here is the output from that command. So this is actually where it breaks down. Didn't do this on my other computer, so I have to do some checking and see what's going on. But then we get another request from the computer or from the client. It's totally appropriate. We generate the next command and we send it, but for some reason the client never receives it. Yeah, it sent the packet and it just sits here and waits forever, waiting for that, because we use that send R, the send receive one. But yeah, so that's how it works. And as you can see, it's just ICMP packets. We issued an ID command. We got the ID back. So that's it for today. Again, another short